These are the kinematic equations slide. So a lot of physics focuses on acceleration, especially when it comes to motion. So acceleration is how fast velocity changes. It is a vector quantity, which means it has a direction. Now, a net force must be applied to an object in order for it to accelerate. And that's what Newton's laws tell us. Now, there are three ways to accelerate. You can speed up, you can slow down, and you can turn. So you can have negative acceleration. Now, since acceleration is a vector, that means it has a direction. So if an object is speeding up, the acceleration will be in the same direction as the velocity. If the object is slowing down, the acceleration will be in the opposite direction as the velocity. And if an object is at rest or at a constant velocity, which is the same thing, the acceleration will be zero. So the acceleration and the velocity are saying, well, notice that that car is speeding up. Well, now the car is slowing down, so the acceleration and the velocity will be in different directions. Well, now the car is going to the left, to the negative side, but it's speeding up, so the acceleration will be negative. So we talk about motion in graphs. So when graphing an object's position versus time, the slope of the line is the velocity. Now, when graphing an object's velocity versus time, the slope of the line is acceleration. Now, think about what slope is, rise over run. So when you're looking at that top one, it'll change in position over change in time. So that's meters per second. So the slope of that line is going to be velocity. And when graphing the velocity versus time, well, the slope is going to be change in velocity over change in time. That'll give you the acceleration. So that answers this question. Well, how do the four conditions of motion, time, position, velocity, and acceleration, relate to each other? So in order to answer this question, look at those slopes even more closely, we did the kinematic simulation. So if we're looking at this, right? So this is that situation that was given, and this is the graph that came with that, the distance from the starting line in meters and the time in seconds. So if we look at this, right, looking at the distance from the start line versus the time graph, well, when was the velocity of one negative? Well, it's going to be when the slope is negative, because the slope of this line will be the velocity. Now, when will it be positive? Well, it's going to be when it's positive. Now, what makes the velocity positive or negative? Well, that's going to be the direction. And when the runner is running to the right, to the positive side, the other runners are moving to the left. Now, where the line is horizontal, well, the velocity is going to be zero. It's that runner is at rest. Now, the next part says, well, this situation was given. But notice, this is the same situation, except it's given from the standpoint of the velocity. So it's just telling that exact same story except from the position of the velocity. It's just describing the slope of that first line. All right. So now, even though you weren't able to manipulate the velocity graph, well, uh, you all you had to do was just make the slope match the what was given to you. All right. So then this was a simulation that was given to you. So explain how the direction of the velocity and the slope of the line on the distance from the starting line versus time graph relate to each other. Well, the distance from the starting line graph relate to each other. Well, notice that the slope of these lines are going to be the velocity, right? Explain how the direction of the acceleration, the slope of the line on the velocity versus time graph relate to each other. So if you look at that chart down below, well, it's speeding up. Notice velocity and acceleration are in the same direction. Now runner two is slowing down, so the velocity and the acceleration are in opposite directions. All right. So answer the conclusion questions, and we've already talked about this. The four conditions of motion are time, position, velocity, and acceleration. Explain how the four conditions of motion relate to each other. Well, the change in position divided by change in time is the velocity. The change in velocity divided by time is the acceleration. So that brings us to, how can motion be described mathematically? Well, that brings us to this branch of physics that we're talking about. It's kinematics, and it's the branch of mechanics concerned with the motion of objects without reference to the forces which cause motion, and focuses on the four conditions of a moving object: time, position, velocity, and acceleration. And we've already seen how they interact. Now, using that interaction and a little bit of calculus, well, these are the equations that we come up with. They're called the kinematic equations. So v0x, that's the velocity in the direction at time zero, that initial velocity. Vfx represents the velocity in the x direction at the end of the time interval, or that final velocity. Ax represents the acceleration in the x direction. Well, delta t is the time interval over which this motion takes place, and delta x is displacement. That's the change in position. How far did this object go during that time interval? Now, in order to solve any of these problems, You only need to know 3 of the 5 variables, and the other 2 can be solved. So let's look at the questions that somebody should ask when they are solving a kinematics equation problem. So the first one is, which variable are you being asked to find? What 3 variables do you already know? And which equation has those 4 variables? So let's look at a practice problem. So Just in Time accelerates his race car uniformly from 20 meters per second to 50 meters per second in 3 seconds. Determine the acceleration of the car during the time interval, then calculate the displacement of the car during the time interval. So the first thing it's asking us to find, well, we need to ask ourselves, what's it asking us to find? Well, the first thing it's asking us to find is the acceleration. Now, what do we know? Well, we know these things. We know the initial velocity is 20 meters per second. We know the final velocity at the end of the time interval is 50 meters per second. And we know delta t is going to, the time interval is going to be 3 seconds. So I can plug those in just to keep everything organized. Now I'm going to look for the equation that has these 4 variables, my 3 known and 1 unknown. It's going to be this equation. So all I have to do is plug everything that I know into that equation, and I can solve for the acceleration, and I get 10.0 meters per second squared. Now notice I didn't just put 10 meters per second squared because, well, everything that I know in the problem has 3 significant figures. So my answer has to have the least amount, which would be 3 significant figures. So now it's asking to solve for the displacement, or that delta x during the time interval. So I can use any 3 of these equations. Now, sometimes it's just use the easiest one, but also keep in mind, if you solve the acceleration incorrectly, you won't get delta x right if you use the second or the fourth one. But if you use the third one, well, it doesn't matter what you got for the acceleration, you can still solve for the delta x correctly. So you plug everything you know in, and you're going to get 105 meters, 3 significant figures. So let's look at another problem, a different kind of problem. So I'm a Hurrian is approaching a stoplight, moving with a velocity of 30 meters per second. The light turns yellow, and Ima applies the brakes and skids to a stop. Ima's acceleration during the time interval is -8 meters per second squared. Determine the displacement of the car during the skidding process, and then solve for the time interval. So the first thing it's asking me to find is, well, delta x. All right, well, I know these 3 variables. I know the initial velocity is going to be 30 meters per second. I know the final velocity, well, she comes to a stop, so it's going to be at rest at 0 meters per second, and the acceleration is -8 meters per second squared. So I'm looking for the equation that has these 4 variables, or I can look for the one that just doesn't have delta t, and that's going to be the fourth equation. So I plug everything that I know into that equation, and I'm going to get 56.3 meters per second squared. Now, when you calculate this, you'll get 56.25 meters per second squared, but just remember the answer has to have the correct number of significant figures. So the least amount in this problem is going to be 3 significant figures. So your answer has to have 3 significant figures, because stop, rest has infinite amount. All right, then it's time to solve for delta t. Well, I can use any of the 3 equations, but if I use that top one, I know that even if I calculated the displacement incorrectly, I'll get the time correct, and I get 3.75 seconds. Notice that it's 3 significant figures. Let's do one last problem. So Ben Russian is waiting at a stoplight when it finally turns green. Ben accelerated from rest at a rate of 6 meters per second squared for a time of 4 seconds. Determine the displacement of Ben's car during the acceleration, then calculate the velocity of the car at the end of the time interval. So the first thing it's asking me to find is the delta x, the displacement. How far did this car go? Now I know the initial velocity is going to be rest. Starts at rest. The acceleration is 6 meters per second squared, and the time interval over which his motion takes place is going to be 4 seconds. So I plug everything that I know in, and I'm looking for the equation that has these 4 variables. Or I can look for the one that doesn't have final velocity. That's going to be this one. So I plug everything that I know into that equation, and I'm going to get 48 meters. So the last thing I need to find is the velocity at the end of this time interval. So I'm looking for the equation, or I can use any of the 3 equations now that I calculated delta x. But if I use the top one, even if I calculated delta x incorrectly, I can still get that final velocity. So I plug everything that I know into the equation, and I'm going to get 24.0 meters per second. Notice that it has 3 significant figures. So just as final thought, remember, there's too much unknown in the universe to take a break from learning. Get out there and question everything.